All right, so Lemma3. So under a linear map, the image of a linearly dependent set is linearly dependent. The proof is really easy. We're just going to suppose that we have a linear combination of vectors, right? v1 through vn, that's equal to the zero vector in V. So we're going to set up this linear combination, and so we're going to assume that some c sub I is non-zero. Then we're going to apply h to both sides. So we're going to take h of the linear combination. Of course, we can split that up into the sum linear combination of the h's, right? So we can take c1 times h of v1 and so on, all the way to c sub n times h of v sub n. And then, of course, if we take h of the zero vector in the vector space V, it's going to map to the zero vector in the vector space W, of course. And so now we have this. We have this linear combination where we have c sub 1 times h of v sub 1 all the way through c sub n and so on. So we have this linear combination equal to this with some c sub 1 not equal to 0, which again gives us dependence. And that's the end of the proof. Okay, so now, when is independence not lost? Well, the sufficient condition is you have an isomorphism, right? But that is also a necessary condition, as we're going to see. In fact, exercise 37 will show you that. So the sufficient condition is to be an isomorphism will give you independence. So you won't lose independence if it's an isomorphism, but it actually turns out to be a necessary condition as well, as you'll see in exercise 37. Now, also, we're going to finish this subsection comparing homomorphisms to isomorphisms by observing that a one-to-one homomorphism is an isomorphism from its domain to its range. So we'll do an example and then we'll introduce another theorem.